Sleeping. That's good. Okay, welcome to the two memory models. My name is Anders. I work at Asenium down in Oslo, here in Norway, and we're working on a new and more performant CPU design, which I think is really fun work. And personally, I mainly work on the performance simulator, so I basically write a bunch of C++ to simulate the stuff, the microarchitecture, and I'm also modeling the memory system and a bit involved in the memory system design as well. I also have this C++ website, a quiz website that some of you might have seen, and there will be a quiz at the party tonight, as well as some other cool party talks. So if you're into quizzes, then join that, and otherwise please also come to the party and just skip the quiz. You don't have to participate. And then, of course, you have to always plug your book, right, when you have a book. And I recently released this C++ Brain Teasers book. So if you're into like learning how stuff works under the hood and like what's actually going on here, I think there are lots of cool details. And there's a discount code for you here if you want that for the ebook. I did bring some physical copies, but they all sold out at the meetup last night. But you can get them in any bookstore as well. Right, the two memory models. Why? So why did I make this talk, and why do I tell myself it's okay that so many of you are in this room now to listen to me talk about this? And what I'm trying to communicate is like a theoretical background for thinking about memory models and giving you some sort of intuition or like a framework for thinking about these kinds of things. So there won't be a lot of practical advice here, but then when you start reading about how do I do this stuff, then like you'll hopefully have some like framework to, oh, this is how I can think about it in a way. And as always with most of my talks, it's just like I wonder how this works. And like I really like figuring out how stuff works. And this is me basically doing this about memory models. And if you actually want some practical advice that you can go back and actually use, then stay in this room because Jana Mashutova is going to talk right after me, and she will actually be giving you like practical advice that you can actually use for something. So yes, which two memory models? Like you probably heard about the memory model in your language. So if you use C++, you know that, well, it has a memory model, and other languages have similar ones. I don't really know C, but I assume it's similar to C++. And Rust, they basically just stole ours because they love all the stuff that we do, and they just copy it. That one is very, very similar. And that's the high-level one. And when you're programming, that's the one you have to think about. When you write concurrent code or anything, you need to think about this because it's a contract between you and the language. So if you code in a certain way, the language promises you then everything will be okay. The other memory model is the one that your CPU or your architecture has. And you don't really need this one. This is what the architecture promises to the language. So if I'm a C++ compiler, I say, well, I promise this stuff to the people that use C++, and then I compile that code for a certain architecture like x86, and then as a compiler, I will then look at the memory model and generate assembly code that can like uphold the things I promised to my user. So that's a contract between the architecture and the compiler or runtime libraries or people that write assembly and stuff. And for high-level models, I will use C++ as an example because it's the one I know the best, and I assume that's the most widespread language between people in this room as well. So, okay, what is the C++ memory model? Let's look in the standard. That's all of it. That's the entire memory model section in the standard. So I blurred it out so you don't start reading it. The point is that this is way too little information, right? That's not the full story. The only thing that the memory model section says is what's meant by a memory location. So basically an int or a float, but not a struct or an array. And then it says that two or more threads can access separate memory locations without interfering with each other. So I have one thread working on some data here, one thread working on some data here. They can just do that, and it works. And that kind of makes sense, right? So if you actually want to know all the things that people tend to talk about when they say memory model, then some other places to read: sequential execution, multithreaded executions and data races, atomic operations library, and thread support library. So if you look in these places, you will gather the whole picture. And then, yeah, how can the compiler promise all of this stuff to me? It uses that the memory model of the architecture it's compiling for. So x86 has one, ARM has one, RISC-V has one, Aptos, that's our CPU, we have one. So everyone has a memory model for the CPU. And you'll find that described in the architecture manual, if you're lucky. Yeah, I'll use RISC-V as an example quite a lot here because it's open source and it's well documented. So it's a nice one to use. I'll also use x86. RISC-V says what is a memory model or a memory consistency model. It's kind of, you can use those interchangeably. It says it's a set of rules specifying the values that can be returned by loads of memory. So that's kind of a nice description, but also it's like it doesn't really tell you that much. But what they're trying to say here is that if you have a load and there have been other stores in the program, in this thread and other threads, like which of these stores should be seen by this load, basically. So that's how they define the CPU memory model. So we have the high-level C++ one and the low-level CPU one. And this is just an overview, and we'll go into details later. But for the CPU memory model, it's very simple if you have one thread. Basically, the only thing you need to think about is if you read some memory and then you write some memory, the read has to return the memory before the write, right? You can't reorder and suddenly you read some memory and then you write to it and suddenly the read actually observed the, like, reordered and observed the write. That, like, things have to happen in sequence. And it's quite easy to define as well, because if you have a program and some input state, there's no UB or anything, there's only one output state. Every time you run the program with the same input, you will always get the same output if you don't have any races or anything. This is single thread, so yeah, that should always happen unless you have bugs. Program plus input state equals output state. If you have many threads, it's more complicated because you can have any valid number of interleavings of the threads. So if you have two threads that write to a variable and a third one that prints it, well, it depends on which order did the threads run in. So you have a program, some input state, and you have many possible output states, depending on the order of the threads. But you have also a lot of invalid output states. So what the memory model says is like which of these possible output states are actually okay according to the memory model. Right, so what has the memory model ever done for me? Like, someone spent a lot of time writing these models, but how do they help me? And that's what we'll cover in this talk, really. Starting with the C++ memory model with some single-threaded examples, a multi-threaded example, and then more formal looking at memory ordering. And then we'll look at the CPU memory models, several variations, including x86 and RISC-V. Right, so we will start with just looking at some single-threaded code to getting us thinking about ordering of things. So we start with a single-threaded example, a silly function that is very useless, but it demonstrates enough things. It takes in two integer pointers. It checks what A is pointing to, stores it in result, adds 1 to that, then checks what B is pointing to and adds that to the result, and then it just returns the sum of whatever A and B are pointing to plus 1. So a simple and silly function. And I've added some pseudo assembly here. So basically, this is not a particular assembly language, just like pseudo stuff. So we load whatever A is pointing to into some register, reg0. Then we add together 1 and reg0, store that in reg0. Then we take whatever B is pointing to, store that in another register, and then we add those registers together and return. Okay, so that's some simple pseudo assembly to do this function here. But then we can observe that loads take a lot of time, right? The load might have to go to cache, that's a few cycles, or it might have to go to like real memory, that's going to take forever. So maybe we could get started on the load a little bit earlier. So if we start the load a bit earlier, like one cycle earlier, maybe the entire function could actually finish a cycle earlier if you just get a head start on the load. So the question then is, could we reorder these two lines? So we start the load before we do the addition of 1. So is it okay to reorder these two lines? And yeah, that's fine. Like, no matter which order you do this, it can't make an observable difference, right? You just start loading and you add something to a completely unrelated register. They're not going to step on each other's toes, so that's fine. Yeah, so we have these two lines, and the thing that says that what the order should be here is the concept of sequenced before in C++. So very many things that you do in C++ is supposed to be sequenced before another thing. So for instance, it says that every value computation and side effect associated with a full expression is sequenced before every value computation and side effect associated with the next full expression to be evaluated. And here you can just like think of everything before the semicolon is a full expression. So everything on line 4, all side effects and value computations are sequenced before this one. So maybe we can't reorder this because C++ says that all the stuff has to happen before the next thing. But the standard doesn't say how you should implement C++. The standard says, here's an abstract machine that I describe. And if you run your program on this conceptual abstract machine that the standard describes, this is the behavior. And any conforming implementation of C++ then has to provide the same output as an abstract machine. So we only need to emulate the observable behavior. So when you actually do the computations, that's not really anything you can observe. So it's not telling you the order that things have to happen. It just has to appear as if that is the case. And observable, that's any input, output, files, volatiles, and implementations can define more if they want. But like, as long as I/O files or volatile accesses are not affected, you can reorder whatever you want in any way. So yeah, we can actually reorder these two lines. So if we look at the assembly here, to the left we have the original, and then to the right we have the reordered one. So the compiler went, let's start the load a cycle earlier so that we can finish this whole thing a bit quicker. Or even if the compiler doesn't do it, the CPU can do that on the fly. So all modern CPUs, basically, maybe some of you are working on some very tiny stuff that doesn't do this, but like all normal CPUs for desktop stuff and mobile phones and whatever, they are out of order. So that means they will reorder your instructions as the program is running, after it's been compiled. But then there's another question. Could we swap the order of the loads? It's not really going to help, probably. It doesn't really matter which one you start first. You need to do both. But could we reorder the loads? So we have this is loaded into this register. This one is loaded into this. Can we reorder those as well? And yeah, in this example here, like no matter which value you load first, it doesn't matter. Like the result will be the same in a single-threaded program like this. There's no way that anything will have changed. Like it doesn't matter. Yeah, and yeah, if you want to know more about out-of-order CPUs, there was a talk last year by my colleague Patrick, so you can check that on YouTube if you want to know more about out-of-order stuff. So what happens in practice? Let's compile this with the latest stable GCC on 03. And then we can see that it did indeed start on the two loads. So these things are memory loads. So it does the two loads first. And then it just does the entire addition in one cool instruction. So yeah, the compiler decided to actually do the loads before the other stuff. So this is fine. These are things you can reorder to speed up your program a bit. So, or not you, but the compiler or your CPU could do this to speed up your program without you even ever noticing. Here's the second and last single-threaded example. Another silly function. It takes in two int pointers. It calls some function defined somewhere that just gets a value, assigns it to result, increments the result, assigns 2 to wherever A is pointing, and then assigns the result to wherever B is pointing. And here's some pseudo assembly. This is like super pseudo assembly, like this one instruction, call a function and put it into a register. But it doesn't really matter. The point is that it represents all the instructions that are required to call get value and put it into reg 0. And then you add 1 to that. Then you do the store of 2, and then you do the store of the result. And then we can observe that, well, stores also take a long time. Can we start the store to A bit earlier? Yes, there are some yeses and some nos. So if you have this assembly here, can we, to be more specific, can we reorder these two? Yes. So the compiler or the CPU can reorder those, so you can do the store first and then the add, because like there's no dependency between these two, so it doesn't matter which order you actually do those. Could you start the store before you call get value? Some yeses and some nos. You cannot do that, because what if get value reads whatever A is pointing to? Now you have stored to get to that value before get value is called, so suddenly you affect get value. So then you might affect the output of the program. So you shouldn't, without knowing what's inside of get value, you can't assume that it's safe to get started on the store earlier. What about the two stores? If you somehow figure out that it's more beneficial to do them in the opposite order, could we swap the order of the stores? Some no's and some, they are both in the original program, they're pointers of the same type. Yeah, so it could be that both of those are actually pointing to the same place, right? You got pointers A and B, but who knows, like they could actually be pointing to the same place. So if you store 2 first and then reg 0, then that memory location is going to be reg 0. If you do the other way around, then that memory location is going to be 2. So if you swap the order of the stores and they happen to point to the same place, you just broke the code. So you cannot swap those. Yeah, and when I say you, I mean like the compiler can't swap the order, and also the CPU has to be careful about not executing those two out of order. So the compiler went ahead and said, well, let's get started on this store a bit early, but then these have to come later. And then the compiler is compiling for some architecture, and it has to make sure that the CPU doesn't do this. So it has to kind of say, hey, CPU, it's actually important here that you don't store to A before you call get value. Oh, and don't reorder the stores, by the way. And how do we express that to the CPU, right? The compiler has to be sure that this doesn't happen. So how does it do that? Well, let's see what GCC does. I just compiled this again with GCC 14.1 on 03. And there's nothing special here. It's just a function call and a couple of moves. So there's no C++ telling the CPU anything about what it cares about ordering. C++ can in fact just assume that this will be fine, because the compiler knows the memory model of x86. And x86 will never reorder 2 stores. So if the compiler emits 2 stores, they will never be reordered on the fly. Same with 2 loads, they will never be reordered on the fly, stuff like that. So the compiler knows that it's fine to just put this stuff out. You don't need any fences or barriers or like stuff. Other architectures like RISC-V can actually reorder stores on the fly. So on RISC-V, these could actually be reordered. But RISC-V is a bit smart about this, so it only reorders stores if they're to different addresses or if the addresses don't overlap. Okay, so x86 says 2 stores, I have to do them in order. RISC-V goes, well, if they're not overlapping, they're going to different places. Sure, then we can, in fact, reorder. And when I say the CPU reorders, that can include like effects from the pipeline, from caches, store buffers, all sorts of stuff inside the CPU that they often don't even tell you about. Like they just have to maintain the apparent order of these things. Yes. So even if I compile this for RISC-V, I wouldn't need any special fences or anything in here, because it checks if they are overlapping, and in that case, it doesn't reorder. Yeah, I guess most people that come to a memory model talk, they are interested in multithreaded stuff. So here's our multithreaded example. This will be a very typical pattern for lock-free code. It's like the canonical example, I think, for lock-free algorithms. And it looks like this. You have some global data somewhere of some type that we don't care about, and then it has a ready flag. So the idea is that the producer will initialize all of that data. That can take a long time. It can be a big thing you have to compute. And when all the data is ready, we set ready to true so that others know that the data is ready. And the consumer can then just, while not ready, just infinite loop until ready becomes true. And then I know, oh, when ready has become true, the data must be ready, so I can use the data. So this seems reasonable, right? And each of these threads are kind of fine, at least, yeah. For now, we can like, yeah, since this we have the sequence before, right? So initialized data is going to happen before ready equals true. So we have the thing we talked about. So if you look at the assembly for the producer, what does it do? It calls initialized data, and only then does it write 1 to wherever ready is. So this is fine, and there's nothing special here. It just calls the function, as sets the ready flag, and since the architecture doesn't reorder stores, well, that's fine. It's gonna all of the stores will have finished before we set ready. And in the consumer, we just loop on. Where's the loop? So the loop just went away. There's no loop. It just uses the data. It doesn't even check the ready flag. It doesn't loop. Like, what's going on here? And you can think about this in two ways. Like, why is the loop gone? Why don't we need this loop? And the informal way is to think about like what could actually happen here in practice. So one thing that could happen when you run the consumer thread is that ready was already true. So it's always true. You don't need the while loop because it's always true. Then if that was the case, you don't need the while loop. Maybe ready is always false. It never changes to true. And then this is actually an infinite loop, and that's undefined behavior. So let's throw it out. Or what the programmer intended here is ready is false, and at some point it changes to true. And then you need the loop. But then you have a data race because someone else is writing to the same variable that you're reading from without any protection. And that's undefined behavior. So then you can also throw out the while loop. So that's like the informal way, like if you go into like a pub argument with the compiler can say, hey, I got this right. The formal way to think about it is with something called forward progress. So the implementation can assume that every thread eventually will take, oh yeah, here's the informal. It's one of those cases. Forward progress. The implementation can assume that all threads will eventually take a step and do one of these things. So the thread will either terminate, do some I/O, access a volatile, or do some sort of synchronization or atomic kind of stuff. So this thread here is not doing I/O, volatile, or any sync or atomic, and it's never going to terminate if this is true. So if this doesn't change, so it violates the forward progress assumption. So that's why it's also undefined behavior, and you can remove it. There's some sort of proposal to be a bit stricter about the forward progress thing. I haven't read it, and I'm not sure if this like applies in this case. But yeah, two ways to think about why is it actually okay to remove the while loop. So how do we fix it? How do we make this non-undefined behavior? What's the smallest change you can think of to make it non-UB? Not volatile. Like what do we want to make atomic? Yeah, we only make the bool atomic, and that's the interesting thing here. So the data is not atomic. It's only the ready flag that is atomic, but still we avoid the any data race. So you fix the data race that we talked about with ready, but you have actually also fixed the data race with data itself. And we're going to explain why it is like that. Yeah, so that's a change we made. And if we now look at the assembly, we can see that the store of the ready flag is now using an atomic operation thing here. It's using exchange to do that. We're not going to talk more about that. And in the consumer, we're actually just using a normal move with the 0 extension, so it's just like a regular move. And then test is basically the spaceship operator for assembly. it checks whether it's 0 and loops. Then it jumps back to the label, and so the while loop is back. There's no atomic stuff here. There's some atomic stuff in the producer function. So okay, we probably fixed the ready thing by this stuff. But how does this fix data? Isn't there still a data race for data itself when we don't protect the data with any mutexes or atomics or anything? So you can have questions like, has the data been initialized? Has it propagated to all other cores? Is it stuck in some cache somewhere? Or like, what could go on here? Is there no data race? So you have all these questions, and like even microarchitectural details we don't even know about, like could affect this. And we don't want to think about all that stuff, right? When we write C++, we don't want to think about microarchitecture or architecture or anything like that. We just want to write the code, and it should work everywhere. So we want a model to think about these things so that we can reason about this just using C++ and like no other questions. And well, what we're interested in, we have this global data and the global ready flag. And then we have like, here's thread 1, it's initializing data and setting ready to true. Here's thread 2, while looping around here and then using data. And then we can just wonder, like, is initialized data happening before use data? So like the inter-thread relationship, is there something that says, well, yes, this actually did happen before the other thing? Or, yeah, and if not, is there a data race? So what's a data race? First, we have to see this thing. So it says 2 expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. So if you have a read and a write to a variable, those conflict. And this is fine. This happens all the time. It like conflict sounds like bad, but it just means like they are trying to work on the same thing. And that can be just fine. There's only a data race if the execution of a program contains, it says it contains a data race if it contains 2 potentially concurrent conflicting actions. So if you have a write and a read and they can happen concurrently, now you're in dangerous territory, at least one of which is not atomic. Okay, so if you have a writer and a reader and one of them is not atomic, and neither happens before the other. Okay, so there are like several ways to get out of a data race. Either make sure they don't happen concurrently, so they're on the same thread, or make them all atomic, like we did with the ready flag, or make sure that one happens before the other. So data is not atomic, and there's conflicting operations on different threads, on concurrent threads. So it must happen before. That's the only way that the data access is safe, is if it happens before the other. Yeah, and any such data race results in undefined behavior. Does the data write happen before the read? And that's the kinds of questions you have to ask yourself all the time when you actually write concurrent code. And you'll get some tips in the next talk about this. But now we want to understand how do we know whether it happens before? So does initialized data happen before use data? Is there a happens before relationship between these 2 expression evaluations? And this is the sequence that we hope for, right? We initialize the data, we set the ready flag, we spin until it's true, and then we use the data. So we hope to get this like inter-thread happens before thing going. That's what we're hoping for. And inside of each thread, it's simple. We saw the sequence before rule earlier. So anything that goes like stuff, semicolon, more stuff, semicolon, it has to be as if that's the order of things. So these 2 arrows are green because like this happened before this and this happened before this. And if we can get a green arrow here, then we're good, right? Then we have this transitive thing. So for this example, where ready is not atomic, the arrow is red. There is nothing saying, and that's like the default. Stuff just happens. There's no happens before relationship unless you can point to somewhere saying, well, this one is actually imposing some sort of order. Otherwise, order between threads is like, I don't know. So in this case, there is no happens before. And then you have a data race, right? You have this both between these two, because this could write and this could read, and they're potentially concurrent, and there's no atomic or stuff. But the same with data. Potentially concurrent access to data. One is a write, and there's no atomic stuff, and no happens before relationship. So data could also then have a data race. And then we fixed it, or I claimed we fixed it by putting stud atomic around the bool. And that does fix it. Somehow this arrow now turned green. So this does in fact interthread happen before this. And then we have this transitive thing. So ready has been fixed, but also data, because transitively through all the green arrows, the data race for data is also gone. But why did the arrow turn green? Is it because it's atomic? So what does atomic mean? The minimum thing that atomic gives you is that it guarantees no half-written values. So if I write a 64-bit word, I'm sure that no other thread can observe like half of that write. If it's atomic, if it's not atomic, it could be that, well, on my architecture, I have to write 32 bits first, and then I write the other 32 bits, and in the meantime, someone read the half-written thing. But if it's atomic, there are no half-written values. And it also says there is a total order to modifications of each individual atomic. So no matter what kind of atomic you use, if one thread sees one order of modifications, all the other threads have to see the same. So if I have like an atomic counter that I go plus plus, so it goes 1, 2, 3, 4, then all threads will also see 1, 2, 3, 4. It can't see like 1, 3, 2, 4. But that's just for one specific atomic. So if I make these two things, I can always rely on for the ready flag. No half-written values, and all modifications to it will be seen in the same order. But it doesn't say anything about the order with respect to other things that happened. So otherwise, it depends, and that's what we're going to look at now. How like the depends part here. What more can you get from atomic except for protecting this single little thing that you're looking at? So here's the same example again. The only thing we did was to change this ready to be an atomical bool instead of just a bool. And this is nice and convenient and everything. You don't change anything in the code, it just happens correctly. But what's actually going on here is this. So equals true. What it means is ready.store true with memory order sequential consistent, which we'll get back to. And then while not ready, it's actually while not ready load instead memory order sequential consistent. So there's a memory order you can give to your stores and loads, and if you don't specify anything, sequentially consistent is the type of ordering that you get. And there are others that we will also look into. Yeah, so sequentially consistent is kind of the strictest, safest, so that's the default you get, but you don't always need it. So you can select others if you want. Sequentially consistent solves a few things. It establishes a happens before across thread. So this is the thing that helps us. This is what turns the arrow green, because if you choose the sequentially consistent memory order, then there is a happens before a relationship between the write and the read of ready. And since we had the other two green arrows, now we have you're on the other, so this way. Yeah, now we have the whole chain, so everything is fine. Even the data is protected by this. But it also imposes a single order to all sequentially consistent operations. So if you have a few threads working on this data that we saw here, and over here some other threads working on some completely unrelated stuff, all of those have to kind of sync up now, because there's one total order to everything that happens to memory, which uses the sequential consistent memory order, and well, usually you don't need that. On the other end of the spectrum for memory orders is the relaxed memory order, and that says there is no happens before relationship. So if I change to relaxed memory order, the arrow is now red again. You can still get the one total order for every atomic, and like no half-written writes apply to both of them, but sequentially consistent imposes a total order to everything going on with memory in your entire program, at least for all the operations that use sequentially consistent. Relaxed basically just means avoid half-written values and that stuff, but you don't have the happens before thing. So that would not work in our example. But for sequentially consistent, we now have, like previously it said ready equals true and while not ready. Now we have what that actually like expands into with atomics, saying sequentially consistent store and sequentially consistent load, and then the arrow is green. I'll just check something. Yes, and if you put relaxed here, there's no longer this happens before relationship. So the thing that makes the arrow green is the memory order, not the fact that it is atomic, but the memory order that we specify for the atomic operations. So then relaxed doesn't work, sequentially consistent does work, but I said that we don't necessarily need everything to be ordered. Like we can look at some things over here, some things over here, reason about those, and it doesn't have to all be ordered. So what we want here is yet another memory order, which is acquire and release. So it says, if an acquire load observes the value of a release store, the release store happens before the acquire load. So if this acquire load observes the write from this release store, the arrow is now green. So yeah, if the acquire load observes the value of a release store, the release store happens before the acquire load. Also, if it observes, that means that, well, this is going to loop 1,000,000 times first and not observe the store. And when the store happens and I observe it here, then I know that this happened before this. So then, so then we have the store happens. We have the happens before relationship, but because the acquire load observed a value from the release store, so then we know that stores happen before load. And so the release and acquire words probably make you think mutex, right? And it's the same words because they're kind of analogous to what you would do with a mutex. You would initialize the data and then release the mutex, and you would acquire the mutex before working on the data. So this isn't a mutex, it's just like an atomic, but it kind of represents a similar idea. So that can be like one way to remember what the release and acquire memory orders mean, because they mean kind of the same thing as the mutex operations. So how does it work then? Like, okay, so the C++ standard says this happens before that, but like, how does it happen before that? So what it says is that if you have a release store, you cannot take any of the stuff of the memory operations here and do them later. So by the time you do this, you must have flushed out all the stuff up here to memory. You can't delay, like the compiler can't reorder anything, the CPU can't reorder anything. By the time you do this, everything must have happened here. And conversely, this has to happen before this. So by the time you have done the acquire load, then you can start on this stuff, but no memory operations from down here can pass up here. And that's how it actually works in practice. So like the standard says there's a green arrow, but in practice what it does is the compiler and the CPU both have to be careful to not order anything below the release or before the acquire. So then all the data has been stored before ready is stored, and ready has been loaded before any of the data is loaded. But the opposite is okay. So if I have some stuff down here, I can actually get started on it a bit earlier if there's some unrelated stuff. So it's like a one-way barrier thing. It makes sure everything is done. Otherwise, I don't really care. And here, make sure you do this before any of this stuff. But if you have some old stuff here that you still want to do, then, well, fine. That doesn't affect anything with the release and acquire order. And I said both the compiler and the CPU has to then conform to this. So here's the way I would actually fix it. I would use store with memory order release and load with memory order acquire, because now as soon as this load observes the store, there's a happens before. So then everything is ordered and there's no data race. Right, so what does this look like? Let's compile it with the GCC again for x86, and we see that now we're actually back to regular moves. So the exchange operation is gone. It's only just moving one into memory here, and then it's moving the ready flag into a register here. So there's no atomic operations here. So even with the release and acquire, where we guaranteed that this must happen before this, there's no traces of anything atomic or like fences or anything. It's just like regular code. If I were to use relaxed, remember I said if I use relaxed here, then stuff breaks. There's no longer happens before. So if I were to use relaxed, look at the assembly code, identical. Identical assembly code for the UB program and the non-UB program. So that can be a bit scary. The reason it works is x86 is super strict about reordering stuff. So the compiler knows that x86 is never going to reorder memory operations anyway, or at least not stores and loads. So like, I don't need to put anything here, says the compiler. But if you as a programmer, you do this and like, let's try relaxed on Godbolt and see what happens. Oh, it's the same, I'll just use relaxed. Now you actually have UB in your program. So that's like one important lesson. If you're doing stuff, don't just look at the assembly and see, well, it's the same, so it must be the same. It's not. Because now we have UB, you could have a future compiler upgrade or something that suddenly causes this to break. Not for this example, but in the general case. And this is why a lot of people have had a hard time porting their code from x86 to like ARM or RISC-V and stuff, because they're used to just, I don't care about this because stuff isn't reordered anyway on x86. And then you compile it on a different architecture and everything is green in CI. And a couple of months later, you have an angry customer at some factory that isn't connected to the internet saying your machine breaks down every second week because it's actually UB. And when you compile it to a different platform, it doesn't work anymore. So if I use release and acquire and compile this to, for instance, RISC-V, I will see some fences in here, which is the compiler telling the CPU that be careful about these particular things. I care about the order. Yeah, there are some other memory orders as well. That's I'll just skip past, I think. And yeah, let's see. Yeah, so how does the compiler know what is safe and what is not? Like, how did it know that it didn't need any fences here on x86, for instance? And no special atomic operations or anything. And that's because of the CPU memory model. So now we kind of leave that. Here is how to think about the C++ way of thinking about memory and the things that give you a framework to think about these things when you actually want to write concurrent code, and move into here's how it happens to work on CPUs. And I think it's pretty cool, but you don't need to know this really. But I always like to if I want to learn something, if you learn the thing that's like one layer below, it's easier to understand the thing one level above. Does that make sense? I think, yeah, I like that at least. So I like to figure out, okay, so what else is going on? So this is what the compiler needs in order to support the C++ memory model. So when we talk about reordering, it could be out of order instruction execution. It could be like micro operations that get reordered, like one instruction turns into many that get reordered internally. Pipeline could do stuff, store buffers, store and load coalescing, memory system, caches, all sorts of things that, again, even as a compiler, I don't want to think about this. I just want to think about the memory model. And for C++, when you think about memory order, you have to think about this expression evaluation and this expression evaluation. Did this one happen before that? And then you can reason about you can zoom in on a little part of your application, and that's kind of the framework to think about memory order. CPU memory models, or also called memory consistency models, they have a different way of thinking about things. So they typically say, imagine that there's a single global total order of all memory operations, like always. What are the allowed orders? So I stole from this book here, I stole this illustration. So imagine you have a bunch of cores, and imagine you have a memory and there's a single bus to the memory. So every core has to take turns. So the memory bus will say, now it's your turn, now it's your turn. So there's no concurrency, there's no caches, nothing. It's just like the memory, and it has one port, and all the cores take turns, and then like after they have taken all their turns, like those turns will have happened in a certain order, and the CPU memory model then says what are allowed orders. How can I put the memory instructions into this total order of things? And then I don't have to think about caches and like all sorts of stuff. So here's the data and ready example that we've been using. This time the data is just like an int or something. So we put 42 into reg 0, store that as data, and then 1 here is true, so we store true to ready. And in the consumer thread we have this wait label. We load ready, and if it's 0, we just like jump around here until it becomes true, and then we load the data and we use the data. So when you want to think about memory order, you can just ignore everything except memory operations. So just ignore the other stuff. What is the order that the memory operations happened? So we have this producer and this consumer, and we have to order all of these. Like these have to have we have to be able to pretend as if they happen in a single order. We have to sort all of these. And what is then a valid order? Yeah, so I think I said already, in the imaginary global total memory order, imagine that each thread takes turns, and then you have like this as if rule. Like they don't actually do this, right? You have all sorts of caches and fancy stuff, but it has to be as if this happens. And then how much of the program order is preserved into that total order? But this is just theoretical model, right? The architecture promises this to the compiler writer or whatever. So here is a possible order. Like here's one way to order these 4 blocks. So if the producer thread runs entirely before the consumer thread, you will have store data, store ready, load ready. Well, it's true, so then we load the data. So this is nice. Like you produce everything, you consume everything, it works. This could also happen. We store data, then the consumer thread starts running. Load ready, it's false. Load ready, it's false. Store ready, load ready, now it's true. So now I can load the data. So this could also happen, and this is also fine, right? The consumer thread doesn't try to load the data before it has actually been stored. Here's another way I can just order these boxes if I want. It's ready. Ready is false. Ready is false. Store ready equals true. Ready is now true. Use the data. Store the data. So this is not what we want, right? But this is also a way to order memory operations. And then what the memory model says is that could this happen or not? Right? The memory model will tell you, is this actually an allowed order of things in the imaginary global total order of things? So if you have sequential consistency, so this is the same we talked about with C++. They use this word, and on the CPU also, there's a sequential consistency, which means everything happens in order, kind of. Then all of program order, so this is the program order, and this is the orange program order, and everything in memory order has to follow the program order. Okay, so if I have store data, store ready, they must appear in that order in the total order. And in the consumer, I do load ready, load data. Then all the load readies have to happen before the load data in this in the memory order. So all of program order is preserved. It's very easy to reason about things because nothing is reordered. Everything has to go in order. So it's nice to reason about this, but you can't really optimize a lot. So no one basically does this. Or maybe again, there's probably some embedded people here who work on some tiny stuff that I don't understand, but like in your phone or your server or laptop, like no one does this. You have to be able to optimize a bit. Because sequential consistency, if you have a load before a load, preserved. Store before a store, load before a store, or store before a load, like all of these program orders must be preserved in the memory order. Nothing can be reordered. So a better way to do things is total store ordering. And that's probably what x86 does. They don't document it. So academics assume that x86 is total store order, and you can just treat it as that, but it's actually never like formally written down anywhere. But the idea that x86 does and other older architectures is they say it makes sense. Like you preserve all of these orders, but I want to be able to delay the stores a bit. And why do they want that? They want to have a store buffer. So if the core does a store and it has more instructions, it can just put the store into the store buffer on the core and just keep running. It doesn't have to wait for this store to go all the way to memory. You're just like, I put it in the buffer and like send it to the cache a bit later. I'll just keep running. So this is a very nice optimization that you can do, that x86 does. So all the stores are buffered inside of the core before even hitting L1. And then you can just like store, okay, put it here, keep running. And then if you have a load to the same address, so I store to address 42, and then I load from address 42, I have to just check the store buffer first before I go ask the cache, because it could be that it's still in my local buffer. It hasn't gone to cache yet. So a later load might then take its value before the buffer is drained to the cache, and then we have to actually check the store buffer. So there's a little bit of like wires to do this, but this can speed up your program quite a bit. And this is the canonical example for TSO. Imagine you have two threads. One is storing X, loading Y. The other is storing Y and loading X. So assuming that both X and Y are 0 when we start, could we see 0 on both sides? And I'll just tell you, because I took quite a long time to to figure out how to think about it. But so imagine Y loads 0. Then X must have been stored, right? This happens before this. So if this loads 0, X must be 0 by now. And if this loads 0, then it means that this store cannot have happened yet. So that means that this happens after this. So then by the time this will also happen after this, which happens after this, so then X must be 1. So you can't, with sequential consistency, there's no way for both X and Y to be 0. And that's often called like a litmus test. So like you say, for my memory order, they can't both be 0. But on TSO, that can actually happen, because on TSO, total store order, stores can be reordered after a load. So in the memory order, like on the core, this is what happens, but the store went into a store buffer and it didn't hit the memory until a bit later. So we can actually load 0 for Y, store 1, and then thread 2 loads 0 for X, and only then do we actually see the store. So the store can be delayed in memory order as opposed to program order. So you can have X equals 0 and Y equals 0, but on TSO, because the store can go after, but on sequential consistency, this is not allowed. And then here's the hard part that confuses everyone I've talked to about this, which includes me and one other person. But that's my data set. We were both confused. What if we both store and load to the same address? And then we say that in the memory order on TSO, the store can be ordered after load in the memory order. So you can, the TSO says you can do this. But then you're like, I load it, suddenly I load it before I store it. So now what's the value of X of the load here? And then the thing with TSO is that memory order describes basically the imaginary order that things hit the caches and like the memory system as like a one big thing. It doesn't dictate the value. So when I do a load, I have to first check the program order on my own core. So if it's actually stored to the same address, the value of the X here is from program order and not from memory order. That might be a bit confusing. So, but like, remember I said it, and then you can think about it later, and then it makes sense. But yeah, so memory order is only about this thing where imagine the memory is a single thing that everyone has to talk to. Which order do things go to that memory thing? It doesn't say necessarily the value of the things inside of the core. Yeah, so the value of load follows program order, otherwise memory order, and yeah, it's just a model. So load X will then just pick the one from the store buffer on thread 1 or in core 1. So then, if you bring up the assembly again that we saw earlier, now we understand why this actually works. Because on x86, we saw it will never reorder stores. So no stores from up here will go below here. and no loads from use data will go up here. So all store-to-store ordering is maintained, load-to-load ordering is maintained. So on TSO, x86, nothing special is needed. Yes. Then we have relaxed memory models. So ARM and RISC-V and others, they then say, well, do you really need to order all the stores and like all the loads and all loads before stores? What if you want a non-FIFO store buffer for some reason? What if you want to coalesce the stores and loads, so 2 stores to the same address can just be sent out as one operation, you save an operation. Maybe you want some fancy speculation and prediction and optimizations in the memory system and cache that, like, maybe we can relax this a bit more. So for instance, if data is not 1 word, but 2 words, so we're storing data 0 and data 1, well, they have to happen before ready, but we don't care about the order between these two. Like if I store half of the data first, later, I don't care. So in the memory order, it's fine to, like, for me as a programmer, as an assembly programmer here, I don't care about the order of the data stores. I just need both of them to have happened before ready, and the same with the loads. So in relaxed memory models, we say, actually, I want the, as a programmer with an interest in performance, I want to give the architecture a lot of freedom to optimize. Only, I want to tell these memory operations I care about. The rest of the stuff, I actually don't care about this. So if you find a clever way to do something, go ahead. And then I want some safe defaults so that it's not impossible to program this thing. And then that's why you need a memory model. So some of the safe defaults on RISC-V, for instance, is that if you have a same address store to store, or they stored like overlapping stores, then you do actually preserve those in the memory order. Because if I store data 0 and I store it again, it has to, like, the final value of this thing has to be reg 1. If this was allowed to be reg 0, it would be just, I had to put fences basically on every other line. That would be impossible to program. So if you do 2 stores to the same address, they won't reorder. But if they're to different order, then they can reorder. And also if you have a data dependency. So in this example, the producer thread loads some data, and then it stores that data somewhere else. So it's take some data, load it, and put it over here. Then there's a dependency between these 2 instructions. If I were to do the store before I do the load, now I will have stored some garbage that was in the register. I won't have stored the data I just loaded. So RISC-V says, actually, I can just figure out there's a dependency, so I won't reorder those, because then everything would be messed up. Yeah, 3 minutes, I'll do one more. So we can have an address dependency. So if you load a pointer to figure out where to store something. So I load the pointer into reg 0, and then I figure out where's the pointer pointing to. I want to store 2 to wherever the pointer is pointing. I can't do the store of 2 until I know where. I have to load the pointer first, so I know where to store it. So here's an address dependency. So that will also not be reordered. So there are some safe defaults like this, and you have other things. If you need more, then you have to put in fences. So what you do is that, like here, I don't care about the order between these 2, but here's a write fence, and then I store ready. So now the CPU knows that there's a write fence, I can't reorder any stores across this fence. And on the other side, there's a read fence, so I can't reorder loads around this. So now I told the CPU that I care about this ready flag, but then I can do like 1,000 stores up here that can do whatever, but then make sure everything is done, and now do the store ready. Yeah, so RISC-V, like you saw, TSO, sequential consistency, the simple one, preserves everything. TSO says preserve everything except you can delay stores. RISC-V says you can reorder whatever. Everything is by default allowed except 13 specific rules. So it has don't reorder across an overlapping don't reorder overlapping stores, the dependency stuff, fences, like it has yeah, just check the manual. It has 13 rules. So like these few specific things save as kind of like the default thing, and then you have to put fences for the rest. So in summary, you as a programmer, you care about like the first part of the talk mainly. You think about the C++ memory model, and you write your programs, and they will just work everywhere. And then the compiler and the people who write runtime libraries and stuff, they have to rely on the architecture memory model that they're compiling for in order to provide the language memory model to you. So the CPU and the architecture provides their memory model to the compiler, which provides the language memory model on top. And the architecture memory model is then implemented thanks to how the microarchitecture works, like pipelines and store buffers and whatnot, and cache coherence. So that's like the actual things that go in your CPU that make it possible to offer the architecture memory model. So if you have two things here to remember, when you think about C++, you have to ask yourself, did this expression happen before this one? And when you think about CPU memory models, just try to remember this figure here, which decides what is allowed. Like there's a single global total order, and what are the allowed orderings in there. And a bonus thing, don't look at the assembly and think that you don't have bugs, because the assembly looks similar, I guess. So yeah, that was my talk. Yeah, so we're actually right on time, so I'm not sure if I can take like 1 or 2 questions. Otherwise, I'll be hanging around. And if you want to use this in practice, just stay in this room, because there will be actual practical advice. Yeah, just feel free to leave, and then yeah, you can just. A fence has to make sure that the local stuff, if doesn't hit the cache yet, or or if you have a store buffer and then you have like a read-write fence, then you can't. Yeah, then you have to make sure that, well, it only has to.